Thank you for being here and to listen to my talk. For me, it's the second time being here in Japan and the first time being in Tokyo. And I must say I'm really impressed about this wonderful city. Of course, most time I spent in the subway, I must say. But yesterday evening we had already the chance to go a little bit outside. So, okay, so you have here a nice university. So I'm impressed, and I heard you have a lot of students also, like we have in Münster. So that's the town I'm coming from the University of Münster. We also have about 40,000 students. So. And I heard at the KU University it's about the same amount. So we have something in common. So your town here, of course, Münster is not as big as Tokyo is, of course. So we are just 300,000 inhabitants. And here I heard you are 7 million or something like that. No? Yeah. So, okay. But I'm not here today to speak about Münster. I'm here today to speak about the diffusion work we are doing in Münster and which we have done in Münster. In particular, I have chosen some examples on diffusion in semiconductors, results which we have obtained over the last years. Some of the work has been also done during my stay at Lawrence Berkeley National Lab a couple of years ago. And as the title shows you, it's diffusion phenomena. I would like to show you some interesting, unexpected diffusion results. And based on these results, you can draw conclusions about the defects which are behind, which dominate or which mediate the diffusion. Because that's one of the things we would like to learn about the diffusion. This is what are the properties of the defects which govern and mediate the diffusion. As you all know, if you are in material science, in order to create functional materials, you have to control the defects in the materials. In the semiconducting area, it's known over several decades that the defects make the play. So semiconductors without defects are not available. So you have to have defects in order to make the semiconductors functional. And so since the defects are very important, you have to find ways to get information about the defects. And one way to learn about defects, in particular at processing temperatures, so what the behavior of the defects is at the processing temperatures, for example, for the fabrication of semiconductors, which are usually done at temperatures well above room temperature, you need the information about what the defects properties are at the high temperatures. And diffusion is one of the methods which gives you some insight into the properties of the defects at high temperatures. And so that's the motivation, I would say, for us looking at the diffusion in semiconductors, since it's basic for the understanding of the properties of defects in order to build up or to create new functional materials based on semiconductors. But of course, you can spend that also for other materials. So it's not related just only for semiconductors. So we in Münster also study glasses and polymers and all the other materials. But also in these materials, defects are very important. But I will keep the talk just to the semiconductors today. Okay, so with this kind of introduction, I would like to give you a little bit more information about what I'm going to talk about. First, I gave already a little bit of introduction, but maybe a more precise introduction on the semiconductors. I make it quite short. And then I would like to tell you some basic experiments on self-diffusion. So self-diffusion is the most fundamental mass transport process in materials. No? So that's the first thing. If you nothing know about any material, the first thing you should do is what is the behavior of the diffusion of the self atoms in the material. That gives you already a first indication what the dynamic in the material is, how much energy you need in order to move an atom from one lattice site to the other. Now, this is a baseline for also then for dopant diffusion and for all the other foreign elements. I will present you some examples on silicon, germanium, and silicon germanium. This is very recent work on these two materials. And results also on compound semiconductors like gallium antimonide and silicon carbide. Then in the case of compound semiconductors, the self-diffusion is already a little bit more complicated than in the case of just elemental semiconductors, but you will see why this is the case. And then I will continue with advanced diffusion studies. By taking advantage of isotopically controlled materials, which are also used in these cases for self-diffusion. But in the case of isotopically controlled materials, you can do one thing which one has never done before, and this is to look how the foreign atom diffusion affects self-diffusion. So you can do it simultaneously. You can look simultaneously on the self-diffusion and foreign atom diffusion, and this gives you much more information than in the case you do these experiments of self and dopant diffusion separately. Okay, and then as a final thing, which is really interesting, and this is just the work, present work. This is diffusion under far away from equilibrium, from thermal equilibrium conditions, and this is diffusion under proton irradiation, or maybe irradiation. Because normally you create defects just by heating, so then you get a thermal concentration, thermal equilibrium concentration of native defects, but you can create defects also via irradiation. Maybe, for example, with proton, electrons, or any other particle. And how this affects the diffusion, so you do an irradiation and the annealing simultaneously, and how this affects the diffusion, I will show you in the case of germanium, where we got very surprising results, which, as you will see, can then be used also for the development of the next generation of MOSFET devices. Okay, let's start. As I mentioned, so what is one of the driving force in the diffusion in semiconductors is still the continuing shrinking of our MOSFET transistor. Here's everybody of you, most of you probably have seen the first transistor. It's a very huge one, and of course you could not make an integrated circuit out of such a thing. It would take maybe more than the building if you would maybe, or maybe I would guess the whole Tokyo if you would like to have the same amount of transistors as in the common microprocessors. Okay, so but you know then. We had the shrinking of the device dimensions. So in particular, so this of course was a point contact transistor. It's the shape, so the functioning is a little bit different from what transistor we have now. This is a so-called, here we have an oxide, as maybe here in the schematic drawing you can see. You have a source and drain, and the current goes in the channel, and the current either on or off will be controlled by the voltage at the gate. And here you have the silicon dioxide or any other high K dielectric. Okay, so this is in 2007. We had this kind of node, 45 nanometer node, and with a channel width here of about 20 nanometers. So this means here the total device is about 45 nanometers. But it still can continue this shrinking. Here are some prototypes of other transistors which are already working. And here you see, for example, one which one would expect in 2011, this size, 22 nanometer process with a 10 nanometer gate. But beyond that date, of course, we don't know yet exactly what will happening. So there are different concepts. As you probably you all know, quantum dots, nanowires, and all these fancy structures which may be used for the future generations, but is not yet foreseen. Maybe what will come. So I expect it will somehow be still going on in this direction with the MOSFET. So since it's not yet clear that this can be controlled in a manner like the fabrication of the MOSFET can be controlled right now. Okay, so in order to start with diffusion and diffusion in semiconductors, of course, it's very important to know what is the structure of the native defects, which of course drive the self-diffusion, mediate the self-diffusion. So the self-diffusion is only driven by the native point defects, and these are the vacancy. The vacancy structure is very simple. You just remove one atom from the lattice. And self-interstitials, in particular in these semiconductors, which are not as dense as, for example, metals. You know, metals have face-centered or they are very densely packed. And there it costs a lot of energy to create a self-interstitial. But it doesn't cost so much energy in the case of the loosely packed semiconductors. Now there you have a lot of space in between the lattice. So you have self-interstitials beside the vacancies, and in that case you have also different structures of the self-interstitial. So this you have to take home. That's very important. And in particular, these are self or an extra atom in the tetrahedral interstitial position. It's indicated here. But you have in the diamond lattice also another interstitial position, and this is the hexagon, the hexa position here. In these here you have a kind of hexagon, and and then there's another one. This is a so-called split interstitial or dumbbell. This is just a configuration where two silicon atoms or maybe two germanium atoms share one lattice site. So these are some different configurations, and you can imagine that it's getting quite complicated in order to predict maybe the movement of self-interstitials, or the migration of the self-interstitials within the lattice, because it will very much depend on what kind of structure dominates. So whereas in the case of a vacancy, it's very simple. It's just a jump from one vacancy, or maybe a nearby atom will just jump into it, and then the vacancy will jump in the inverse direction. But here the movement of a self-interstitial is already a little bit more complicated. I will not go into that detail on that in order to, because one can spend 1 hour just on the migration of the different species here. But just to tell you that there is something hidden in the movement of the self-interstitials. Okay, in the native point defects in 3-5s, as I mentioned, so there you have so you have two sublattices. So there you have to distinguish between vacancies on, for example, on the gallium sublattice and the vacancy on the arsenic sublattice. In the case you have gallium arsenide or antimony, so then on the vacancy on the antimony sublattice. And the same for the self-interstitials. You have to distinguish between the self-interstitial from group 3 element or from the group 5 element. And you have in addition so-called anti-site defects. Fortunately, anti-site defects do not contribute to self-diffusion. So in the self-diffusion, you can forget about that. So it would be too much. The energy for self-diffusion via anti-site would mean you have a direct exchange of the atoms. But if two atoms are sitting, maybe an anti-site on the lattice position and another, and they have to share their place, there's no space. There's not enough space. So the migration energy is quite high. So compared to the migration of vacancies and self-interstitials. So therefore, these contribution due to the anti-sites in self-diffusion you can neglect. So this means self-diffusion in compound semiconductors is also mainly described by vacancies and self-interstitials, but you have to take in mind that always two of these species can contribute on either sublattices. Okay, let's start simple. Self-diffusion in silicon. As I mentioned, so vacancies and self-interstitials are in diamond structures the main defects, and so it's not a wonder that both defects contribute to self-diffusion. And here I have schematically shown such an interstitial, a vacancy, and if you measure the silicon self-diffusion coefficient given by this depends on two contributions, a vacancy contribution and a self-interstitial contribution. Here I give you maybe an idea how the self-interstitial can migrate in the case of self-diffusion. So what you are going to see will be a molecular dynamic simulation of the migration of the tetrahedral self-interstitial, which I just have introduced, to maybe from this side. Here, these are just indicated the nearest neighbors. This is the tetrahedral interstitial, and this will go via a so-called split interstitial in this direction. So here will be formed a split interstitial first, and then it will go to the next tetrahedral position. So you see here then already a sequence of how the movement of such a tetrahedral interstitial will take place in the self-diffusion. But just for this species here, as I mentioned, there can be also an hexagonal interstitial and also a dumbbell. And they have a different migration scheme. Where's the mouse? It goes, as always, very fast, so maybe I repeat it once. Oops, 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 oops. So you see here first, no, that's the interstitial, and then look at here, this area. There will be the split interstitial, and then finally, now you have a split interstitial, and now you end up here with the other tetrahedral position. So this is a kind of visualization of how the self-diffusion of such an interstitial can take place. Okay, so in order to do such kind of self-diffusion experiments, so what we use and also you use in your group are isotopically enriched materials. So we take advantage of the possibility that, for example, silicon-28 isotopically enriched is available, or silicon-29 or silicon-30. And based on these isotopically enriched materials, you can grow such kind of isotope heterostructures. And one of our first experiments, so there we got from Isonics, from Steve Burden, epitaxial layers of silicon-28, 5 micron thick, so quite thick, and on natural silicon substrate. And here the Escrow structure as a SIMS analysis is shown here. And these kind of sample you just have to anneal. And here are some examples at very high temperatures here, because you have a thick epi layer on top, you can anneal at very high temperature. And then you end up with such kind of diffusion profiles. At that time we also had other isotope samples with a thinner isotope layer and also sandwiched between natural silicon, and based on these samples we could determine here the silicon self-diffusion coefficient, shown here as the open symbols. And recently here in your group, Yasu has determined, so has extended the self-diffusion experiment by means of Raman investigations on multi-layer structure, also silicon isotope multi-layer structure, and what he had done a kind of Raman scattering. And from the decay, because if you do an intermixing, you determine that the periodicity in the Raman signal, so you have due to the periodicity of your isotope structure, you have a certain Raman signal, and if now an intermixing takes place, the Raman signal decreases, and this you can use in order to determine the diffusion coefficient. And this has been then extended in that range here, and based on these results, you have determined the vacancy contribution to self-diffusion with an activation enthalpy of 3.6 eV. Okay, now everybody can learn, okay, that's the story for the silicon, but presently in the collaborative research, we are checking the low temperature data again with another method, with neutron reflectometry and advanced SIMS techniques. So we will try to extend even more the temperature range in order to see whether the activation enthalpy is correct, because these bear some problems with dopant diffusion, but I will skip these details here. Okay, so I already mentioned this kind of approach with neutron reflectometry. So that's in principle it's a method similar to Raman. So this we have already used in order to determine the diffusion, the self-diffusion in germanium at low temperatures. The high temperature self-diffusion has been done already 20 years or 25 years ago, but the problem are always the low temperatures, because there the diffusional broadening is very, very small. So we also use such kind of isotope structure. And the reason is, like in the case of Raman, that the neutron scattering length is different for different isotopes. So maybe in the case of germanium-70, the neutron scattering length is higher than in the case of a natural germanium. And this means if you have a periodicity in the germanium layers, maybe alternating germanium-70, natural germanium, you have an artificial lattice. And this the neutrons feel, and so you get a Bracht peak due to the periodicity of this ordering of this isotope structure. And this is shown here. So this is the Bracht peak due to the neutron, due to the different scattering lengths of the neutrons in the germanium-70 and the natural germanium. So the first order peak, third order peak, and now usually one analyzes the decay of the first order peak by annealing such an isotope structure. So if you anneal it, of course, there will be an interdiffusion of these different isotopes, and this you will notice in the decay of a Bracht peak, of this Bracht peak here, which is shown here in magnification. And here are some temperatures and times, and it depends on how strong of the interdiffusion is. The more pronounced is the decay of the peak. So, and based on this, in principle, simple method, we could extend the self-diffusion down to low temperatures. And here in the case of germanium, this wasn't a big surprise, because we know that the vacancies in the case of germanium dominate the self-diffusion, so the contribution of the interstitials is very, very small. It's very likely it's not detectable, because the formation energy of interstitials is too high in the case of germanium. Okay, but it was kind of a proof of principles that the method is very nice in order to determine self-diffusion at low temperature by means of neutron reflectometry, and this method will be now applied to silicon. And this is the ongoing work right now we had together here with Koei and Münster. Okay, so self-diffusion in silicon germanium. So it's getting more and more complicated. So we had such kind of isotope structure. So silicon germanium X means the different alloy compositions. So with a small X silicon rich, with a high X germanium rich. And we have a so-called graded buffer layer. This means that the structure here is the isotope structure. Here you have a natural composition of silicon germanium. Here you have the isotopically enriched, both in silicon and germanium. And the graded buffer means this structure is relaxed, so there is no strain effect on the diffusion. That would be another thing which one has to determine after the self-diffusion is settled. Not to start with everything simultaneously, self-diffusion and strain, then it's getting difficult to figure out what the intrinsic self-diffusion is. So therefore we decided first to start with this experiment. Okay, here are already some of the profiles, how they look like after thermal annealing in comparison to the S-grown. Here for 5% germanium, here on this side for 70% germanium. You have nice profiles which can be very well described with a solution of 6-second law based for self-diffusion, and the solid lines are here the best fits, and based on that you can determine the diffusion coefficient. And as usual, the diffusion coefficients are always illustrated as a function of the inverse temperature, which is shown here. Here you see also again the X with 0.05 for 5% germanium, here for 0.7 for 70% germanium. And if you may look a little bit carefully, so red always means silicon, blue always means germanium. So you see here at 5% germanium in the silicon germanium. The silicon and the germanium diffusion is very, very similar, also in magnitude. But now with increasing germanium content, the diffusion of germanium gets faster and faster compared to silicon. Now you see here the difference here increases. Even in the case if you consider the pure germanium self-diffusion compared to silicon diffusion in germanium. So here the distance, from here to here, the distance increases. So first, of course, you can say, okay, silicon diffusion is always a little bit smaller than the germanium diffusion, and the activation enthalpy is similar, but it tends to be of silicon to be slightly higher. Yeah, and from this kind of behavior, we already can tell what is going on, and this means that the silicon in silicon germanium has the tendency to repel a vacancy, and the germanium would like to be situated in the close, or the vacancy would like to be situated close to a germanium or in a germanium-rich environment, and that's the reason why the germanium diffusion tends to be higher than the silicon diffusion. And this has been in the meantime also confirmed by theoretical calculations. Of course, you can do now ab initio calculations on the stability of vacancies as a function of the nearest neighbor occupation. And this has been done. Okay, so you get information now on the composition dependence on the self-diffusion. Here's the activation enthalpy as a function of the germanium composition. Here are the data for the silicon diffusion, again red, and the germanium diffusion, again blue. So what you can clearly see from our results, we have a so-called upward bowing behavior compared to the recent, to the earlier experiments. Here, these were the earliest experiments from McVeigh. They use polycrystalline silicon germanium structures, very likely dirty. Zangenberg, they also use the epi layers, but with very thin layers of silicon germanium, and Strom et al. So they have used the radiotracer technique, but these results are likely affected due to surface effects, because they have to sputter. So they have measured the self-diffusion right at the surface, and we have it in the buried interfaces. I will not go in, but so there are some reasons here why these data are not as accurate as the data based now on these isotope superlattice structures. Okay, so this kind of composition dependence is very it's kind of interesting, and but it seems to be that this is a kind of general behavior for the silicon germanium system. For example, if you look in the literature, you will also find for antimony in the silicon germanium that it shows such an upward bowing, so as we have here in the self-diffusion. And also if you do theoretical calculations on the stability of so-called E-center is nothing else than the dopant vacancy pair in the silicon germanium, or like shown here, so the arsenic vacancy and the phosphorus vacancy pair as a function of the germanium concentration. Also this stability in terms of the binding energy of this pair also shows such kind of upward bowing. So it seems to be a general trend for the silicon germanium system having such a dependence on the germanium concentration with an upward bowing. Okay, so now we have seen self-diffusion studies in silicon in germanium, silicon germanium, and now we go to the 3-5s. So, and as an example, I took out the diffusion, self-diffusion with gallium antimonide system. The reason is here we have a very nice system where you can determine the self-diffusion both on the gallium sublattice and on the antimony sublattice, because there are in both cases two stable isotopes available. This is different in the case of gallium arsenide. For example, arsenic is the only stable isotope, so there is no second stable isotope in the periodic table available. But for gallium, as you see, two. But in the gallium arsenide system, we also have done the gallium arsenide self-diffusion, but I haven't put that into the talk. Okay, so the same approach. You have here natural gallium antimonide substrate, here buffer layers, and here, as already introduced, the isotope structure with the two different isotopes, and then again the cap layer. it's always a big advantage to put a cap layer on top, because then you can have the self-diffusion buried at buried interfaces. And you are far back, you are away from surface effects. Okay, here's a SIMS measurement of the S-drone structure. Here for the gallium, 6971, and here for antimony, 121 and 123. Now you do the annealing. The melting point, by the way, of gallium antimony is very low, 712 degrees C. So you are here 12 Kelvin below the melting point of gallium antimony. You see a very nice broadening on the gallium sublattice, but in comparison to the S-grown structure, no significant broadening on the antimony sublattice. Okay, so this was already very surprising, and so now I did these experiments in Berkeley, and then I made a couple of measurements, maybe several hours, and then finally I decided, because I never saw a movement on the antimony sublattice, okay, now I anneal for a very long time. And then finally, after 18 days, 12 Kelvin below the melting temperature, I finally saw a movement on the antimony sublattice, but it's very, very low. So this here is an example which you probably have never seen, that there's a material system which is on one sublattice. It's very, very, the self-diffusion is normal, very, very fast, no? Close to the melting point, but on the other sublattice, nothing is happening. It's stick, so the antimony atoms don't move. Don't like to move. So that's really fascinating. No? Now, thinking about, maybe you are an antimony and you have always 4 gallium in your surrounding, and the gallium are running like crazy, and you are sticking there and and say, okay, you may run, but I stay here. It behaves like this. Okay, and this is shown in such a temperature dependence of a diffusion coefficient. It ends up that the antimony diffusion coefficient, even close to the melting point, it has a diffusion coefficient of 10 to the minus 18th in centimeters squared per second. It's very, very low. And the gallium behaves normal. So here are some literature data based on Rayleigh tracer measurements. They have a very nice big scatter, and it also the earlier data told that the antimony and the gallium self-diffusion should be similar. No? But this is totally wrong. It can't be. No? The reason tracer self-diffusion, they measure it from the surface. If the surface is decomposing during the annealing, then you have a problem. No? Then you measure what else, no? But not stoichiometric material. Okay. So, but we need an explanation why this is happening here. Why is the antimony diffusion so low at even close to the melting point? Yeah, the reason is for this that because you can say that already immediately, if it's low, there must be no defects on the antimony sublattice. If you would have vacancies on the antimony sublattice or antimony interstitials, then you should have a movement. But if the movement is very, very slow, there are no defects which mediate the diffusion on the antimony sublattice. And that's the reason. So looking, for example, for antimony vacancy, so the energy to create such an antimony vacancy is higher than the energy you need to make the transformation from the gallium vacancy to a gallium antiside. So maybe if the antimony sublattice tends to create a vacancy, no, then you have surrounded by 4 galliums, then the system feels, oh, it's much more convenient that the gallium jumps into the antimony vacancy, creates thereby a gallium antiside, and leaves behind a gallium vacancy. That's much more favorable. And the same for the interstitial antimony. It doesn't like, because it's a very big atom, it doesn't like to be in interstitial. So then it searches for a gallium vacancy. And if it comes along, then an antiside defect is also formed. So this means these two reactions have a consequence that they remove the defects on the antimony sublattice. And as a consequence, there's no self-diffusion. In the meantime, after we have published that in Nature, these have really high disparity between the self-diffusion on these two sublattices. There were some theoretical calculations on the stability of these, and this has been confirmed what I just mentioned to you. Now you can do then ab initio calculations in order to check what the energy balance is of such kind of transformation reactions. Okay, so this was a very famous and very interesting example on what can happening in the case of self-diffusion and what kind of information you get out just by doing self-diffusion measurements. Okay, another thing, self-diffusion of silicon carbide, that's very, very tricky. Silicon, you know probably silicon carbide has a very high sublimation point, so it doesn't melt, it first will decompose at 2450 degrees C. In order to do self-diffusion measurements, you have to go to very, very high temperatures. And that's a challenge. And we have such an oven, it's like a cooking oven. Here in the center you have a carbon crucible, and in that carbon crucible you put in a silicon carbide crucible, and in that silicon carbide crucible you put your silicon carbide sample. And what we use also in that case, isotopically enriched silicon carbide, which we got from a company from the United States. So here's the Escrow Analysis. So we have it isotopically enriched in carbon and also in silicon. Here's the Escrow structure. And now you can use that also for self-diffusion measurements. But before you use that, you have to take care about your surface. And this was one of the problems we had at the beginning, because if you anneal, you have to anneal at very high temperatures, 2200 degrees C, you get a very worse surface. Because we would like to do SIMS, and if the surface gets rough during the annealing, there's no chance to get an accurate SIMS profile. So you have to find a way to protect the surface, and what we have done is in principle, it's very simple. So we have spin-coated a photoresistant, and this photoresistant you then anneal under argon atmosphere in order to decompose the photoresistance and end up with a graphite layer on top of the silicon carbide. And then you can do your diffusion annealing at temperature above 2000 degrees C. And then after the annealing, you remove a graphite layer just by burning it under oxygen atmosphere at lower temperatures. And then you end up with a very nice smooth surface, which you can then use. Then you can use that sample for SIMS analysis. So that's a trick, but without that trick, you would not be able to do any self-diffusion measurements. Okay, diffusion of carbon, I make that story short. So here you see the profile which we have determined, recording the fit. There are already data in the literature. This would you expect on self-diffusion in carbon if the literature data would be correct. So it should be almost homogeneous after where's the time indicated? No, it's an hour here, after 6 hours at that temperature. So we got data which are 6 orders of magnitude lower compared to the literature values. The same in the case of silicon. So this is the work, this is our work, and here it's about 4 orders of magnitude lower values than what one would expect in the case of Hong et al. Of course, the reason is also at that time, it was 81, the quality of silicon carbide was not as good as it is today. And yes, as a consequence, here are the diffusion coefficient as a function of the inverse temperature. Now one can do, of course, this just gives you activation enthalpies, and now in order to determine what kind of defects are behind, what kind of defects mediate the diffusion in the case of carbon in silicon carbide and silicon in silicon carbide, you have to do additional experiments. I haven't put these details into the talk, but you have to do then dopant diffusion experiments, for example, boron we have done, and phosphorus diffusion experiments in silicon carbide, and looking how these dopants diffuse and making a comparison with the self-diffusion, we can say that the carbon diffusion is mediated by doubly positively charged carbon interstitials, and the silicon diffusion is mediated by singly negatively charged silicon vacancies. So vacancies on the silicon sublattice. I skipped the details about this. This would take too much time in order to explain that. Maybe you get a little bit on feeling on the next slices, for which are coming now. It's fine? Okay. I mentioned in the introduction a little bit on advanced diffusion studies. So self-diffusion studies are in principle simple. You got already a little bit the feeling that the interpretation can be complicated and you need some other additional experiments in order to figure out what are the defects which mediate the self-diffusion. This kind of information you get more directly if you do advanced diffusion studies taking such kind of isotope multi-layer structures and doing not only self-diffusion but at the same time dopant diffusion. So now what you can do, as indicated here, you have such a structure with a multi-layer, so you have alternating natural composition and isotopically enriched compositions. Maybe you may put an amorphous layer on top and implant a dopant of interest into the amorphous layer just in order to avoid implantation damage here in the crystalline structure. And then you can use such a sample for dopant diffusion experiments and how the dopant diffusion affects the self-diffusion. And this we have done in the case of silicon first as a kind of illustration how powerful this technique is in order to determine the native defects and in particular the charge states of the native defects, because all vacancies and self-interstitials, they can exist in different charge states. They may be neutral, singly or positively charged. No? Okay, so this is how the experiment looks like. Here you have already the S-grown structure, so concentration versus depth, the color as before. As I mentioned, the amorphous layer you can use in order to deposit your dopant of interest by implantation. Here arsenic, but you can also do boron or phosphorus as we have done. Yeah, and then you do an annealing. Okay. Of course, maybe first a little bit on what may happen. Dopant diffusion, I have kept it very simple. Just the vacancy mechanism. X may be the dopant. Here's a vacancy, so a dopant vacancy pair. And if this dissociates, you will end up with a substitutional dopant and isolated vacancy. Or the interstitial C mechanism, you have a dopant interstitial pair. And if this dissociates, you end up with these two isolated defects. There are, of course, other mechanisms also operative, but these are the most important ones. Okay, and now here are the results of the simultaneous diffusion of arsenic and silicon in the silicon isotope multilayer structure. Now here again concentration versus depth. You see here the distribution of a silicon. You already notice here that the broadening is not homogeneous. You see here more pronounced broadening than deeper in the material. You see here the arsenic profile. This is here the amorphous range, so this is the region where you have the implantation. This is a kind of source region for the arsenic. Yeah, and now of course in the fitting of these kind of diffusion process, you have to do the modeling of both the self-diffusion and the dopant diffusion. And here you can already see, based on the broadening here, it's more pronounced than here, that the defect, the native defect, must be negatively charged. So here the dashed line is shown, which shows a homogeneous broadening. What you would expect if all native defects would be neutral, then the broadening should be homogeneous. So you can say directly, okay, there must be a native defect which is negatively charged. No? Because here you have a N-type dopant. It drives the Fermi level to the conduction band, and if the Fermi level is close to the conduction band, it favors negatively charged defects. And this you see then directly in the self-diffusion. Okay. Okay, you do the modeling. The modeling gives you also information about the supersaturation or undersaturation of vacancies and interstitials. In the case of arsenic, this is close to the equilibrium. It depends on the diffusion properties of arsenic, but I will not go into that detail now. Okay. The same you can do for boron. Here's the boron profile. Here's the silicon profile. Again, the dashed line shows what you would expect if all defects would be neutral. Here you have a more pronounced broadening also under p-type doping. This shows you that there are also defects which are positively charged. Yeah, you have here a supersaturation of self-interstitials, corresponding undersaturation of vacancies, and the colored curves are the best fits based on the simulations. Yeah, and we have also phosphorus, but I will not go into that detail. But from the whole analysis, you get then diffusion data, of course, for the phosphorus, boron, and arsenic. For intrinsic conditions, you can rescale that. And more importantly, you get the information about the charge states of the various point effects. So what you see here is the energy. Here's the energy, so the band gap of germanium as a function of the temperature. Of course, if you increase the temperature, the band gap will shrink. And here you have the position of the various native defects, which we determined from the simultaneous fitting of all profiles. So in order to get that out, you have not only to simulate boron and the corresponding silicon diffusion, but you have to simulate all simultaneously. Boron diffusion, silicon diffusion, arsenic diffusion, silicon diffusion, phosphorus diffusion, silicon diffusion at a certain temperature. Because by arsenic, phosphorus and boron, you move the fermion level in the n-type doping to the conduction band, and in the case of p-type doping to the valence band. And so you need all these kind of behavior in order to get that out precisely. Yeah, and based on this, so these are then as a function of temperature, but we can show here how the level ordering behaves. So we have, in particular, we could determine a kind of negative U behavior, so that's more favorable that the self-interstitials are double positively charged, and we have contributions of a singly and doubly negatively charged vacancy with energy levels very close together. And yeah, and with this kind of information now you have tools at hand in order to make predictive simulations of dopant diffusion in silicon under various doping levels. Now this, for example, is a very useful information for process simulators. Okay. Mechanism, now I skipped the silicon, and you can do similar experiments in the case of germanium as we have done recently. And in the case of germanium, again, you may have these mechanisms, the vacancy mechanism, which is mostly dominant, and the interstitial C mechanism, I already introduced that. And here are the elements which diffuse via the vacancy mechanism. Here are the n-type dopants. And the germanium, they all diffuse via the vacancy mechanism, but also the p-type dopants diffuse via the vacancy mechanism, except boron and carbon. People believe, and I believe, it could be very likely via the interstitial C mechanism, but it's not yet proved fully. It could be also explained by the vacancy mechanism, but it's very likely that they move via the interstitial C mechanism. So first give you an idea about the donor diffusion in germanium, which behaves a little bit different to the case of silicon. So a simple experiment would be you have a piece of germanium, no? And you make, for example, here, what is it, arsenic. Maybe you apply a certain pressure of arsenic in the surrounding. No? That means it depends on the amount of arsenic you offer in your maybe diffusion ampule. You may have a very high pressure of arsenic or a low pressure of arsenic. And depending on this activity, due to the pressure of arsenic in your ampule, you can adjust a high concentration of arsenic at your surface of germanium or a low concentration. But here you see it's the same temperature of annealing. So then you take this temperature and this time, and if you have if you establish a very high surface concentration, you get this profile. If you establish a very low concentration, you get this profile. This profile is a complementary error function, and this is a so-called box-shaped profile. But you see immediately it's totally different, the profile shape, and also the penetration depth is totally different. And this, of course, one has to understand, and this you can explain fully just on the basis of a vacancy mechanism by taking into account that the arsenic vacancy pair is singly negatively charged. It must be singly negatively charged. And of course the substitutional one would be positively charged and a double negatively charged vacancy. So the reason for this increasement in the depth is related to the difference in the charge state of these two defects of the E-center and of the substitutional dopant. It's in the case of germanium, it's a factor of it's 2 difference. In the case of silicon, by the way, it's just 1. So in the case of germanium, dopant diffusion is much more enhanced under high doping conditions than in the case of silicon, and this is a very big problem in the technology right now. Okay, so that's then the functional dependence of the dopant diffusion under extrinsic conditions under high doping levels that it goes with the square of the free electron concentration. Okay, and then you can do much more fancy experiments. Again, with isotope structure, I just introduced it also with the case of silicon. So you have a multi-layer structure of germanium-70, but in this case here we have additionally, in the case of germanium-70, in that area we have a carbon doping. Carbon at concentration of 10 to the 20s. And the carbon solubility in germanium is pretty low, but here we are well above the solubility limit. And if you have a carbon inside, you see what is happening if you then do diffusion of arsenic. Here's the Escrow. No? You have implantation of arsenic, and then you do it, and then you do an annealing step. You see that the arsenic segregates in the area where you have the carbon. The self-diffusion on the germanium is shown here. It's already very, very strong intermixing of the germanium lattice. But the carbon, you can see here, is the carbon distribution is the same as in the Escrow structure. And you observe here a segregation of arsenic due to the carbon, and you also see a reduced penetration depth of the arsenic profile. So it's at the same temperature and time, and this profile here is just for comparison how the arsenic profile looks like in natural germanium, just without carbon. So this is what you would expect if you have no carbon in your germanium. Okay, this is already a lot of information, and now since you have here additionally a carbon inside, which, as you can see here, due to the segregation, acts as a trap for the arsenic, you have to invoke additional reactions in order to explain this behavior of arsenic diffusion in the isotope superlattice structure with the carbon inside. Yeah, and of course this is the vacancy mechanism, and then here we have to invoke a reaction with carbon. So of course the mobile species is always the arsenic vacancy pair, and this combines with a substitutional carbon to such an immobile complex. And what you also have, maybe you cannot see that here, you have a so-called deactivation reaction. So just due to Coulomb attraction, this negatively E-center, this negatively charged pair tends to form a complex with the positively substitutional dopant. And this ends up with a neutral defect, which of course is then missing in the activation of the arsenic, which is also a problem right now for the technology. Okay, now you can do a simulation based on this model, and yeah, it's very, very, it explains the experimental results quite well. And what we can say from that, that these carbon E-center clusters, they retard the diffusion of the n-type dopings, and but we have a disadvantage, so that this kind of cluster formation, of the neutral cluster formation, this is not suppressed by the carbon. Yeah, maybe from the technology point of view, of course, it's people don't like the very strong diffusion of the n-type dopants in germanium. So therefore, this is in principle an advantage that the carbon retards the diffusion of the n-type doping. And we're thinking about MOSFET structures, maybe source and drain regions, and you will shrink also in future of this structure. You would like to have very shallow penetration depths. Maybe if you think about a germanium transistor, maybe as 50 years ago, but not with the contact transistor, but in the shape of a MOSFET structure. So with a source and drain, you need a very shallow dopant profile. and high doping concentrations. And in the case of germanium, with n-type dopings, you end up with under these conditions with a huge diffusion of the n-type dopings due to the high diffusivity under extrinsic doping conditions, and this you can avoid a little bit by the carbon, by co-doping with carbon. But unfortunately, the deactivation, which also takes place, this cluster formation of the neutron cluster formation cannot be suppressed with a carbon. So that would be not the solution in order to realize an N-channel MOSFET just based on germanium. Okay. So this is now the last thing, one maybe at the end, one also quite surprising thing, and this is, I keep it short because I know that maybe it's, the time is running. So the diffusion under irradiation. So this is in comparison to what I have shown before, this is a diffusion under non-equilibrium conditions. Non-equilibrium conditions means you are far away from the thermal equilibrium concentration of self-interstitials and vacancies. All the experiments I have shown before, there you are pretty close to concentrations of self-interstitials and vacancies being in thermal equilibrium. No? But here you produce your vacancies and self-interstitials athermally. Now what you do, you are hitting your sample with protons in our case, but you can also use other particles. And they lose energy on their way through the sample and create Frankel effects. So they create vacancies and self-interstitials to the same amount. That's important. No? Under thermal conditions, of course, the amount can be different. But here you produce vacancies and self-interstitials to the same amount with huge concentrations, much higher than the thermal equilibrium concentration. Okay. Warming up a little bit, a fancy sample holder. Here's the graphite, here's the sample, here comes the proton beam. The graphite holder here is heated from beneath. Here's the thermocouple to check or to control the temperature. You have to make a shielding and isolations and electron suppressions and all these things in order to be able to measure the beam current. And another important thing is that these samples which we use have to be very thin in order to make sure that all protons go through. If they wouldn't go through, you would end up with so-called end-of-range defects. At the end, if the protons lose most of their energy, you get a huge amount of defects inside. Okay, so you have to thin them down to about 30 micrometers in thickness. Okay, the holder is a little bit tilted in order to prevent channeling. No? And usually we take protons of 2.5 MeV and a proton flux in the range of 1.0 to 3.8 microamps. Yeah, and here, so now you can ask yourself, yeah, how the self-diffusion in germanium is affected by irradiation. And for that we use different isotope structures, a so-called thick isotope structure. This means that the total thickness here is in the range of 1.2 microns. So you have each layer is 200 or something nanometers in thickness. And we have also a thin germanium isotope structure. So here the whole structure is just 300 nanometer in thickness, on each layer about 15 nanometers. But what you notice already, that the broadening after irradiation at this temperature and time for the thick isotope structure and also for the thin isotope structure is homogeneous. So you get the same broadening here and there, here and there. So it looks like self-diffusion under normal thermal equilibrium conditions. This was really unexpected because, as you know, a surface, which is here, acts as a sink for vacancies or for native defects. No? So you create the native defects here inside to a concentration well above the thermal equilibrium concentration. Of course, at the surface, you establish the equilibrium concentration. because there you can't create any native defects, no, because it's a surface. And so you should expect that the native defect concentration decreases approaching the surface. And this you should then expect, so therefore you should expect here a less pronounced broadening close to the surface, and then a more pronounced broadening of the isotope structure the deeper you go into your sample. But as you see, the experiment tells you another story. It's a homogeneous broadening. We have done the same experiments with silicon. There it behaves normal. So there you get here a gradient. So here the broadening is not as pronounced right to the surface. So here's something going on. So the same, yeah. Okay. Here's the result of our fitting of our idea, how to explain that. Again here, so what you see here, the red ones are again the sample annealed and irradiated. So you see the homogeneous broadening as I just mentioned. But the same sample, in the same sample we also have an area which has been covered by the carbon plate. Maybe you have a sample of 5 × 5 millimeter square, and then you have a window of about 3 millimeter in diameter, and then the outer part of your sample is then covered. So you can make 2 SIMS measurements from the covered area, not proton exposed, and from the inner area, proton exposed. And the inner from the outer area, so there you have the normal thermal broadening, and the inner area gives you the proton enhancement of the self-diffusion. But as you see here, it's always homogeneous broadening. Of course, for the thermal one, it's not unexpected, but here it's again unexpected. Yeah, and in order to get the good simulation out of it, or maybe in order to explain that, we have to assume that the germanium surface is a sink for the vacancy, but is not a sink, that's important, not a sink for the self-interstitials. So you can only predict such kind of broadening under irradiation, such kind of homogeneous broadening in the case the surface is not a sufficient sink for one of the native defects. And we propose that this is the self-interstitial. And why it is the self-interstitial, I will convince you in the following. So what you see here then now, based on this assumption first, you end up, if the surface is not a sink for the self-interstitials, you produce them all the time during irradiation here in the material. The concentration goes up. The vacancies the surface acts as a sink. They are annihilated not only by the self-interstitials but also at the surface. So you end up in steady state with a vacancy concentration very close to thermal equilibrium and an interstitial concentration, 9 orders of magnitude higher, almost 10 orders of magnitude higher than the thermal equilibrium concentration. But of course we have to prove this, and one thing is to see how boron behaves under irradiation. And this is shown here. Again, you have a sample, a part of a sample covered, not exposed to the proton, the other part exposed to the protons. So the red one is the profile of boron after the proton irradiation, and the blue one is just the profile in the covered part of the sample. So the covered part of the sample reflects the S-grown profile of boron, and the red one, so you see a very strong enhancement. Under normal thermal temperature, under normal thermal equilibrium conditions, boron doesn't want to move. It's a very, very slow diffuser in germanium. It's even slower than germanium self-diffusion. But under irradiation, it goes like crazy, as you see here. But you also see here some spikes left. These are very likely some precipitates, which we have to determine by TEM in the near future. Okay, so what you can take with you, so you see here the boron, diffusion of boron is clearly enhanced under proton irradiation. This would be the case just for thermal, and this is then under proton irradiation. You have also a homogeneous broadening. There's no gradient. And since the boron doesn't move under thermal equilibrium, this is the first hint that the defect behind is a self-interstitial. But it's not a clear proof yet. In order to make the proof of principles, maybe you remember that the dopants, the n-type dopants, like phosphorus, for example, they move via phosphorus vacancy pairs. So now what you have in our scheme, in our understanding, in these experiments you create a supersaturation, a huge supersaturation of self-interstitials. If that would be true, one would expect that the diffusion of phosphorus is retarded under irradiation, because phosphorus goes via vacancies, and if you create by irradiation a huge concentration of self-interstitials, you avoid the formation of phosphorus vacancy pairs. So the formation of these pairs will be then suppressed, and as a consequence the diffusion of phosphorus should be retarded. And this, of course, has never been observed, that maybe a diffusion of an element under irradiation is retarded. Usually you think everything is enhanced. No? So maybe you can tell me, but I'm not aware of any element which goes slower under irradiation. Okay, so let's do this experiment. And as you see, it really behaves like this, of course. Otherwise, so you see here that phosphorus is really strongly retarded under irradiation. And this is really the proof of principles that you have self-interstitials under irradiation and not vacancies, which make the game. Okay, so here you see what profile you get in the covered part of your sample. So it's always the same sample. You have a covered part and the part exposed to the protons. The covered part behaves normal. So this solid line here is what you would expect based on the phosphorus diffusion data which we have analyzed before, just for thermal equilibrium conditions. And then in the proton exposed part, you see it's a very strong retardation. And at the same time, you also see a higher concentration, higher electrical concentration of the phosphorus. So that is, of course, a very, very important result. So that it's first, of course, from the basic understanding that there's something which also goes slower under irradiation. The people would not do annealing under irradiation simultaneously because they would have thought, okay, then everything goes like crazy. But it's not the case in the case of germanium. Okay, so what you have, as I mentioned, the formation of these mobile phosphorus vacancy pairs, they are effectively suppressed by the presence of the self-interstitials. It's very simple. You have this guy here plus the self-interstitial, and then you keep it substitutionally. And and also here the steepness of the profile also indicates you that the electrical activation here is higher than under irradiation than if in the case you don't irradiate. Okay, so here are the three evidences coming up that the self-interstitials are important under irradiation, and this is first the self-diffusion enhancement and homogeneity in depth. That was the first indication. Then the Born diffusion was enhanced and homogeneous in depth. This gives a hint of this reaction. And finally, that the phosphorus diffusion in germanium is suppressed. It gives hint to this expression. And of course, very important, which you keep in mind, that the self-interstitials, for some reason, don't like the germanium surface. No? So they avoid the surface. That's also a very fundamental thing, maybe for theoretical calculations. What may be the reason that the self-interstitials, if they are created in the bulk, why they would not go to the surface. So, and as a consequence of that, that the self-interstitials avoid the surface, they stimulate an interstitial-mediated diffusion under irradiation. So in the case of germanium, you have under thermal equilibrium, everything is going by vacancies, and under non-equilibrium conditions, everything is going by interstitials. And that's very interesting, also from the technological point of view, because now you can switch between a vacancy-controlled diffusion mode and an interstitial-controlled diffusion mode. So everything what is going under thermal equilibrium conditions via vacancies will not go under irradiation conditions. Everything which is mobile under thermal equilibrium conditions is not mobile under non-equilibrium conditions. And that's really nice. You can switch the mobility of the defect just by irradiation. And with that, I'm at the end. I hope I could convince you a little bit on the scientific issues of diffusion, so that it provides really in-depth information on material properties, like the type of point effects, the charge state, reaction mechanisms, and all these information you get out from these diffusion studies are very valuable for comparison with theoretical predictions. This is, if you look into theoretical papers on ab initio calculations on the stability of defects, they do a lot of comparison with diffusion data. Okay, and the technological issue, which I kept a little bit below this, of course, in particular, these diffusion studies, they provide, on the other hand, strategies for effective diffusion doping. And in particular, the last thing you saw with the switching between a vacancy and interstitial diffusion mode is very, very promising for the fabrication of a fully germanium-based N-channel MOSFET, which could not yet be realized due to the enhanced diffusion of the N-type dopants and the strong deactivation of the N-type dopants under high doping levels. But with the switching, which you have by the irradiation, so if you now do an annealing under irradiation, you can suppress the N-type doping diffusion and you get at the same time a higher activation. Thank you very much.